Oh, cool. Hi, guys. Where's slides coming? Yeah, there you go. Hi, I'm JJ. I'm a engineering director at DeepMind. It's my first time being that role. I've been an engineer my whole life, so it's a work in progress here. But I lead the applied group at DeepMind, based here in Singapore, which is kind of lucky because I think that we actually have some really fascinating problems that are unique to Southeast Asia, and Singapore in particular. Luckily, DeepMind decided to open an office here, which meant that I get to work on all these problems. And so I wanted to talk a little bit about what we do at Applied AI. The whole idea, to really sort of summarize this, is we try to push the boundaries on what the models do. It's kind of a hand-wavy term. So to nail this down a little more specifically, the models do a specific thing. They have a set of inputs and a set of outputs, right? It's a typical thing. With language models, you have an input prompt, and then you have output tokens. With a video model, you send in a text prompt, and you get a video. What we try to do is take it and make those models do more than they were originally intended to do. And so a great example here is like with VO. It's a video generation model, right? So you prompt it, ask it to do something, and it generates 8 seconds worth of video. What happens if you need more than 8 seconds? Our group really focuses on what happens when you really try to solve a business problem, and 8 seconds just isn't enough. I can't really think of a whole lot of businesses that benefit from an 8 seconds worth of video generation. That's neat and it's fun for a demo, but if you're a movie studio, you might want to generate a whole scene. Maybe you want to generate an entire episode of a TV show, or maybe you want to do an entire feature-length film. Unfortunately, generating an entire feature-length film from 8-second chunks is not just like running the same thing over and over. It's actually a lot harder than that. And so what my team does is we try to figure out how to make those things work. And as you can see on the screen here, like we're not focused just on Gemini and Gemma, like our text models, or even just Nano Banana, which does image generation, or VO, which does video. We also explore more natural science-based things. So for example, AlphaFold generates protein predictions. AlphaGenome sequences genes. WeatherNext tries to predict the weather. An example here is, the WeatherNext is trying to figure out what the weather is going to look like, but it's trained off of data around the world. Singapore has weird weather. I don't know about you guys, but I get hit with surge prices on Grab all the time from these flash storms that show up all the time. Like it's actually really hard to predict the weather here. These monsoon season is just it's kind of crazy. Well, how do you use a weather prediction model to help you figure out what you're supposed to do with your, when the weather's going to happen, if it's not trained on that data? And so we explore things like that. I think there's kind of two key takeaways that we're going to talk about here. One is a problem, one is an answer. So if you're going to leave right after this, these are the two slides to care about. One is the pattern we keep seeing over and over and over is we're asking the model to do way too much stuff. We give it this big, scary problem. We hope that it's going to do the right thing. And when it doesn't, we get kind of irritated at it. And we say, why is this model so dumb? And we kind of forget that like a year or two ago, the models were like terrible in comparison to today. They're amazing now. These AI models do amazing things, but we still get frustrated with them. And so the key takeaway that we've seen in our Apply team is that instead of breaking the model down into pieces, we're just sort of throwing a big, scary problem at it and then hoping for the best. And we've found that just doesn't work. You can't just call VO 100 times, 8-second chunks each, and stitch them together. You will not get what you want, right? You need to break it down into smaller pieces and then have the model solve that. And you can even have the model help you do that. And so instead of trying to rely on these language models as one giant problem solver, what you kind of need to do instead is take it, break it into chunks, and then you wrap it in sort of more deterministic things of how to execute and solve your problem. So we'll come back to this at the end, but these are really challenging kind of problems that ultimately you can't just throw at the model. Maybe one day, like let's be honest, maybe the models will be even more incredible. We'll get to AGI tomorrow, and then this whole talk, you can ignore it. But as of today, I don't think there's a model out there that you can just throw a big, scary problem at it. Even Fable and Mythos, like it's just, you can't do that. You have to break it down a little bit. So usually we have to think about these problems, and I kind of have to stop the talk here because a lot of the work I do is like super confidential. Luckily, I was able to announce something pretty recently. We announced it at I/O, and so I'm actually allowed to talk through an example, so I'm really excited. Just out of curiosity, how many people vibe code in some capacity? Like fire up. Okay, some people. I will try not to be too overly technical. I'm an engineer, so I kind of fall back into that, but bear with me here. So one of the problems that we tried to solve was this idea of if you're a runner and you can't see, you want to go running, the way to do that is you call a friend and you have a friend be your running guide. So if you're a blind or low vision athlete, to go for a run, you need to get a friend to go with you, which means you need to find time on your calendar, find time on their calendar. Everyone needs to be available. Then the weather needs to not be awful. There's a whole bunch of things that happen. Now, some of them we can control, some of them we can't. But the thought was, what if, hypothetically, instead of having a human be your running agent guide, we could have a phone do it? What if we could strap something to, as a harness on your chest, and you could go running, and you have a pair of headphones. You can see the orange-looking headphones there. And it could guide you on how to navigate a track while you are a blind runner. So what I want to do is show you a little bit of what we ended up coming up with, and then we can go backwards a little bit, and I'll tell you all of the crazy ways that we tried not to throw this big giant problem at a single language model and hope for the best, but instead broke it down into smaller bits surrounded by determinism and ended up with something that actually worked. Because let's be honest, if there are no requirements of safety or latency, you can absolutely throw this at a language model. All these models are great. You can throw them an image and they'll tell you what's in the image, right? But how do you do it quickly? How do you make sure that if this person is running and there's an obstacle that they're not going to fall over and seriously injure themselves? Like the stakes are a little bit higher than just sort of a web app that we're running at home. People could be injured, so we have to be careful about this. So I have a short video. It's just like a minute long. And I think if I hit this button, it'll play.
It's 28 degrees and clear. Perfect running weather. Let's do a slow run. And I'll guide your pace with audio cues. Whenever you're ready. Great rhythm. Keep that stride. There's some gym gear on your left. Stay on your current track. Left turn coming up. Ease into it. You've got this. And now, take it slow. You got room.
By pairing...
Sorry, that audio was a bad clip. So what's happening in this video is actually really cool. You couldn't hear it. There's actually a three-dimensional sort of beacon beep. So the headphones that he's listening to is not just the guy saying there's a gym bag on your left, but there's actually like a noise that he hears, like a beeping sound. I'll get into that in a second. That it's sort of a follow the beep sort of sound. If you ever played Marco Polo, anybody? Same idea, just a lot more complicated. And so to do this, we actually had to do an immense amount of work. It wasn't just throw it at the model and hope for the best. So we had three kind of key pieces of varying degrees of importance. So the first piece is the sound of the guy's voice, the running agent, saying things like, stay in your current lane, there's some gym gear on your left, stay on this track, that's a good pace. This was the idea of a running agent. And that is, in this case, it was Gemini 2.5 Flash that was generating the voice. Live that was generating the voice. It could also be Gemma with a TTS sort of sandwich around the side. But the idea was that it sort of understood the conceptual things that were in the images, and that was running a standard language model image understanding path, right? So what it was doing was given a frame from the camera that was strapped to his chest with this harness. It was able to look at the image, look what was in there, see things, and say, oh, that's a gym bag, and it's on the runner's left. And it helped them understand what was going on and guide the run itself. And so this is, in my view, the least important part. It's nice. It's great to say that there's a gym bag on your left, but it's kind of more important that I know if there is an anything right in front of me. That's just feels like it's a little more critical. And so we have this piece that's sort of step one. That can go off on the internet because the latency is not as important, right? We can wait a little bit. And we'll see a demo of exactly when that sort of manifests. The other two pieces are about safety. And they're sort of the most important part. So this planner agent is sort of the more important, the fun interactive part. The top part is the more important part. That's understanding what's going on in the space, identifying obstacles, and identifying the track. So that means we need to understand what is on the track and what is off the track. When my engineers were demoing this, a couple of them fell off the track. We blindfolded people and tested it out, right? It was a fun little experience. But we have to understand both where the track is and whether we're on it, and then guide the runner on the right path, as well as if there's anything in the way. And both of those are very, very difficult. Oops, that's the back button. OK, so on this case, this is an example of a runner. And in understanding, let's say that we know where the track is, we needed to figure out how to tell the runner, hey, this is the way you're going, without really messing up and confusing them. And so what we did was we made sort of a beeping tick sound. You'll hear it a little bit later in one of the videos. I'll try to play it, and hopefully it'll come through on the speakers. But the idea is, if you're aimed in the right way, and we can tell this by looking at the segment that we have, then the beep will sound as like sort of a tick, tick, tick. And then it gets a little deeper as you veer off to the side. This might sound a little difficult and crazy, but we had the runners showing up, like snapping at the floor and using echolocation to figure out where they were. It was amazing to see these runners and how they navigated already. This made a lot of sense to them, and it was quite easy. We up the pitch higher or lower if you start to veer far off the track. So if you're veering far down, right down the center, right, we break it up and we understand this beacon. So the yellow dot is the beacon, and you can see it. This is the mobile app that's running on the phone here. You can see the blue parallelogram is the segment that we've identified as the track, and the yellow dot is sort of the target. And you notice it's a little bit to the left because we've identified a turn up there. And so the idea is, like, we can understand where the segment is, and then we can play these beeping sounds to tell the runner that they're headed in the right direction. And we change the sort of ticking sound based on how they position themselves, where the camera is aimed. And it turns out to be really tricky because there's lots of edge cases, and we have to break this down. There's our beeping sound. Let me try and see if I can make that go again. So that's the everything's fine, you're on the right track beep. Again, this might sound a little weird to a lot of us. When I was testing this out, it's very confusing. For these runners, they got it right away, and it was really straightforward. So we're working with sort of a different group of accessible folks who can do stuff. So the whole idea here is now we have to figure out, how do we draw this blue parallelogram? It's actually quite challenging. This is not a typical output from something like Gemini or Claude or ChatGPT. Like, that's not very normal. What we ended up doing, because the latency requirements were so serious, it had to be fast, is we trained an on-device segmentation model running through the TPU on the Pixel phone. So what that meant was, given an image, we had trained it to understand what was a running path and what was not a running path. And then we helped them to draw this sort of blue parallelogram using the lines on the running path to start, as well as some understanding of the trajectory, the entire sort of red parallelogram here. So we kind of grabbed the lane that the runner is in the middle and understood the entire structure there. And then we use that to figure out where to put the yellow dot. And once we have the position of the yellow dot, we know which sound to play. Same thing goes if people start veering off to the side. We know, because they're aimed off to the side, that we should play a different sound because the dot is not sort of showing up where it should. And so we play a slightly different sound. Let me see if this comes through. See how it gets sort of lower and further away and the ting sound disappears? That high-pitched ting sound is the good one. That means like you're on the right track. As you turn to the right, we can see, there you go. The angle goes over to 20 plus, and we lose that ting because the yellow dot is not aligned with that blue parallelogram. It's off to the far left side, not straight down the middle. And so by doing this, we're able to understand where the runner is, how they're positioned, and most importantly, exactly the direction that they're taking. And in this case, they're going to run not only off their path, but if they keep going, they will slam into a wall. Or in our case, we had some people in Woodlands who fell into a little ditch. They were okay. Everything was fine. But these things are serious safety concerns. So this was not a case where we wanted to use a large language model. We wanted something more predictable, lower latency, more durable, something that we could fine-tune and train on different running tracks. It made a very big difference. So we had to use the right ML model for the job. And in this case, it turned out that the language model was not the right one. Here's how this looks. This is on the left an animation of a runner here in Singapore. No, sorry, this is actually in Thailand. And you can see the numbers are changing as there's sort of variation as they sway, because when we're running, we don't go straight forward. We tend to veer left and right. And so on the left and right, you have these green progress bars, and the bars are sort of saying how far off track you are. And we use use that to calculate our percentage degree off the center dot. And we keep redrawing this very, very fast. The whole idea is if we can pump through 50 frames per second through this model, that's great. Like, we can make sure that people stay on their track and play a very accurate sound all the time. Here's another live video of this. This one's in the US. Same idea. You have these two things on the side, and it didn't play the beeping sound, but that's going through the headphones. We had a similar and very confusing problem when it came to depth perception. And we'll see this out. There's a video that I can play to show this. Understanding that something is in the way is different from understanding what is in the way. If there's a gym bag on the left, that's something that a really intelligent visual image understanding model can figure out. But that's not the same thing as knowing that something is there. That's a lot. They're two different classes of problem. Knowing that it's a unicorn on the left versus a horse compared to there's something on the left, one's a much easier version of that problem. And so what we had to do is realize that we didn't care that it was a gym bag on the left necessarily. That's nice to know, but that's not the important information. The important information is you are going to fall down because you're about to crash into a trash can. Very, very different kind of situation. And so we try to use something, first, obviously using Gemini, but that was too slow, right? Because we need super fast latency. And so we looked at, okay, what can we do on device? Yet again, let's fire up the on-device TPU and run another model. This model was a depth perception model, which if you can see here, there's little squares with numbers on them. It's a little blurry, and you'll see it a little later, but each one of those squares represents a guesstimate of how far away that given position in the image is. So red means very close. That's the closest that we have in that. And the dark blue, indigo, kind of black almost, that means the furthest away. There's a couple things to note here. One is the very bottom is not shaded, and the other is the very top is not shaded. That was on purpose. We started out with the entire thing shaded, and then we realized that that didn't give us enough detail or granularity on what exactly we were looking at here. Because the sky is kilometers away, and so that would show up blue, and the space right in front of us is very close, so that would show up red. So then something a little bit in front of us would just sort of show up as a little bit red, and you couldn't really tell the difference between it. So what we realized was we don't care about the very bottom. This bottom section that's not striped, that is the you're already going to fall down, we can't do anything about it. Like, that's what that region is. And I'm sorry, like, you shouldn't get there, but that's what it is. The top section is, well, that's not a problem yet. Like, maybe something's going to fly across the screen, but like, it's too early to say. And so by chopping out those two sections, what we end up with is sort of the critical region. And in this critical region, we get really much more clear estimations of depth, and then the differences between something showing up that you're going to run into, it becomes more apparent. I don't know if you can see that there's a cone in the middle of the lane right over here. And so I'll hit play here, and you can see the cones coming up. It's going into the blue section, and you can, oops, sorry. Oh no, I messed it up again, didn't I? There you go. Okay. There's no pause button on this. So you can see the cone sort of shows up, and then
Stop.
Obstacle ahead.
Two things to note here. As you can tell, the very, very intelligent Gemini agent told us that there was an obstacle way, way, way too late. We had already hit it by then. The stop was our local text-to-speech running off the segmentation model. And so it led to a really interesting case where we could see everything, and you can hear the difference between the latency and why it matters so much. But most importantly, because we only take this little strip, we realize that everything is sort of, if we don't have that strip, that we don't have the clarity. If we do have segmented into the critical range, we can have the visual clarity. You might think like, oh, wow, that was some fun cases. These are just two of the like really, really egregious cases. We had probably dozens of edge cases because that's what this world is now. It's easy to get to 90%. The language models, like we could use all the Claude Code and Gemini Coder and Anti-Gravity and GPT Codex. They will get you 90% of the way there, and they're amazing. All of them are like truly amazing. But that last 10% is incredibly difficult. Another example here before I wrap up is if you're running and you swing your arms, the models will think that you're about to hit something because it sees an obstacle and it doesn't know that it's your hand. So we had to retrain the model again when we realized that like somebody's leg was coming into the way and the arm would come into the frame. And it was like yet another of these problems that we ran into. It just kept getting, like, so you can see a foot there. These are obviously like exaggerated movements, but the concept remains the same. Like, you don't realize the last 10% is so complicated until you get there. Now, the good news is the models get you most of the way there very quickly and with really high quality code. But until you really dig into it, it's actually a really big problem. And so we had dozens of problems like this and had to work through them all. And so my big takeaway here is it's really important to break down these incredible models, use them for what they're good at, and not try to use them for what they're not good at. Gemini is great at at understanding images, right? But it's not great at being super fast and understanding obstacles coming up for a blind runner. So our sort of recipe here from these types of projects is generally, one, when the LLMs make sense to use, we use them. They're awesome. They do amazing things. It's like truly incredible. We use them for reasoning. We use them for language understanding. We use them for classification on sort of fuzzy categorization problems, for text generation, image generation, media generation. We use these models. They're awesome. They struggle with determinism. They're unpredictable. They hallucinate. They lie to us. They don't mean to, but they do. And so when you can route things properly, when you can use a segmentation model that's a little bit more deterministic, when you have super high latency constraints, you don't use them. You use something else. And lastly, the glue that pulls it all together is we use the coding agents to help us build all this stuff, right? When you don't know which one to use, ask the fuzzy agent and it'll tell you which one is a better fit for this whole thing. Like, that's the magic of these AI tools you have online and offline, and they all work. So I guess the big takeaway here is, like, we can't just tell the models, hey, give financial advice to my customers and please don't break any laws. Like, that's definitely not going to work. Instead, you have to break down the problem. You have to take it in small pieces and use the models for what they're good for, and use other models or deterministic code for what that's good for. So thanks so much.